Yeah, we call it recursion. And yeah, cool. Today I will talk about the social level analysis. Most of the people will call it SNA. Just do a quick survey. How many of you have heard about social level analysis before? Okay. How many of you actually have done some social level analysis?
I want to try.
Oh, you want to try? Good. Most of you don't. Actually, for this talk, the purpose of this talk is give you a taste of what is the social level analysis, and I hope that this talk can convince you that the social level analysis is actually very important, and maybe some questions in your field of research you will need to use the SNA, and then you may also want to try it with R, and R actually provide a lot of facility for doing the SNA. And the agenda for today is just a very brief and super superficial introduction of the SNA. And I will present a case of SNA, and then the code is actually available on my GitHub. For those who are reading from YouTube, actually you can scan the QR code to get the slides. And before we talk about SNA, SNA stands for social level analysis. And we need to talk about what is social network before we go on to talk about what is analysis, the social level analysis, this analysis part. A social network, usually people will call it a graph. And graph is not the general meaning of graph, it's the mathematical meaning of graph. It can be like most mathematical things. It can be summarized into a very beautiful equation like G equal to V and E. And the G is graph. And but most of the people, like me, will not understand what is G equal to VE. So this is what most of the people understand about a social network, right? It's a graph like that. And the V is actually the vertices of this graph. We just meaning the circle in this social network. And for example, in this graph, we have 6 vertex, so that we have 1, 2, 3, 4, 5, 6, the vertex of these graphs. And then the E is actually stand for the edges. Edges is the relationship between 2 vertex. For example, there is a connection between 1 and 2, so that we have an edge of 1 and 2. And also 1 is also connected to 5, so we have another edge which is 1, 5, and so on. Okay. And because there is a different field, the mathematician usually call them the V and E as a vertex and edge. And computer scientists create a different kind of terminology. They call the vertex looks, and the edge, they still call it edge. Some people call it arc. I should be classified as a social scientist. So when I read the paper, they usually call the vertex actors and the actors as ties. But most people, like me, actually, I don't like to call those things actors and ties. So I just follow the computer scientists and call them looks and edges. And in the following talk, I will use the look and edges. But in the documentation of most of the software, they use the vertices and edges. But in this talk, I will use the looks and edges. And I want to give you an example. For example, we have some people from 3 different bands, music band. Okay. Paul is a bandmate of Ringo, John, George, Chris, and Dave. And another set of relationship is Kurt is the bandmate of Chris, Dave, and Pat. And also Dave is the bandmate of Let, Taylor, and Chris. And we have the text description of all these relationships. And then we can represent it as a network because we have these people in the network. So we have Paul, George, Ringo, these people. And then if they belong to the same band, they have an edge. There's a relationship between each other. So we have these kind of edges. Say Paul and George is a bandmate, so they actually form an edge between these 2 people. And if you represent it as a graphic, the relationship actually look like this. And this is a very complicated relationship, and if you understand the music, actually this is actually 3 different bands. For example, the Beatles, the Nirvana, and the Foo Fighters. They have a very complicated relationship, and using the SNA, the social network analysis, we can understand more about the relationship between the people in this complicated network. And in the previous example, the edges have no direction. For example, you be friend with somebody, and there is no direction, right? For example, I friend with Fan, and he will be friend with me as well. So it is something I expected. But for example, in Twitter, the relationship between the people is not undirected. It's actually directed. For example, this is my Twitter account, and I follow some people. I follow like Dropbox or GitHub, but people from the account GitHub may not be following me. This is not a bidirectional relationship. And but for people like Guy Freeman, he follow me and then I follow him, so there is a bidirectional relationship. And it is happening something in Twitter, but in Facebook it is not directed. But in most of the real life application, the social network is mostly directed. Okay. And these are other social network applications that you may use the social network analysis in them. For example, the gene expression network. For example, when gene A express, it will generate protein X, and then with protein X, protein Y, it will regulate another gene called gene maybe B, and then it is a complicated network, and you can use a directed network to represent this kind of relationship. And food web is an application that you can use in ecology. And actually, I'm a biologist by training, and my major is ecology. And I use the social network analysis to analyze the food web. For example, the grass is eaten by those grasshopper, and then the grasshopper is eaten by frog, and then frog eaten by dog, and maybe human being. We eat the dog, yeah, something like that. And the relationship is directed. So we need to represent that kind of relationship using directed network. And legislator network is something the people from the open data. They are doing something related to the Legislative Council in Hong Kong. So they are trying to analyze the legislator, whether they will vote the same moment together. So they try to analyze it as a network as well. And a co-author network is an undirected network, because if I co-author write a paper with you, this is not a directed relationship, right? But for citation, it's a directed relationship, because I cite your paper, but you may not cite my paper, right? So it is directed. We used to have some transportation workers in this R user group. So he may try to analyze the transportation network using social network analysis. I think the transportation network is directed, but it may not be true. I don't know. So we talk about how to represent some relationship using a social network, but how to actually represent a network. For example, you have some data. How to make them a social network that can be analyzed. There is two ways. One is called the adjacency matrix. Another way is called the edge list. And for example, these undirected graphs, we can represent it as an adjacency matrix, which is, for example, you have 6 nodes here, right? And the adjacency matrix will be a 6x6 square matrix. And for example, 1 and 2 have a relationship with each other, right? So when you look up the 1, 2, there will be 1 here. And also, if you look up, say, 4, 3, and it will be 1 here also. Okay? Another way is called the edge list, which is, if you understand the matrix, there is a sparse representation of a matrix, right? The sparse form is usually occupy less memory, right? Because you don't need to record the pair that have low edges between them. So for, let's say you just need to represent the network as just these very small matrix, but you still representing the same network. Okay. But for directed graphs, the relationship will be a little bit different. You usually represent the row as the destination and the column as the source. So, for example, the 2 and 1 is actually a bidirectional relationship. So you look up the row 1 and the source 2, it have a 1 here. And if you look up the column 1 and row 2, it also have a 1 because it's a bidirectional relationship. But if you look up 5 to 1, you need to read the column 5 and 1. Column 5 and row 1 is have a 1 here. But if you look up the column 1 and 5 is 0. So, and you can also represent it as a edge list. In most of the time, you will enter your data as an edge list, and then you import it into R as a graph. And you may wonder why there is a third column called weights there, right? For graphs, for a simple graph like this, all of them, the weight will be 1. But for a complicated network like this one is a transportation network. It representing how I go to work from my home in Yunnan to Hong Kong U. And there is a weight there, which is the money that I need to pay for that particular mode of transportation. For example, when I need to go from my home to Yunnan, it actually costs $6.5. So I need to represent it as a weight here. Okay. For example, in your Facebook friends, you may need to pay more, make the rate between you and your wife higher, right? The rates will be higher. But for some friends that you only meet once, that rate will be much smaller, right? We call it weak ties. And how to represent social network object in R? There are actually two different packages for doing that. The first one is iGraph. iGraph have the beauty of building everything in one package. For example, when you need to do porting that particular social network object, and you need to do social network analysis, you want to do anything, for example, community detection, iGraph has everything. And there is another package called Network, which is part of a project called StatNet. And this network package will only do one thing: is the representation of a social network object. It will do nothing else. If you need to do analysis on that social network object represented by the network package, you need to use another package. But in this particular example, I will use iGraph because it is easier in some sense. And for example, I create a data frame called eList, which is actually representing the edge list with something like that. But actually, it is just a data frame that look like this, which is actually our edge list. For example, 1 to 2 will be the weight 1. And then we use a function called graph.dataframe, and to change this data frame into a graph or a social network object. And we need to specify it as a directed network. And this graph.dataframe function, it will treat the first two columns as the information regarding the relationship, the edges, right? And any other columns as the weight or the edge attributes. And after you convert, for example, we convert the edge list into a social network called example. And then we can actually plot this example, and it will plot that particular social network, like we do in the previous graph, in this graph. Actually, this is the same graph that we plot here. Okay. And after we talk about how to represent social network, the next thing is we want to analyze that social network, right? And there are 3 different levels of analysis: and graph level, the look level, and the edge level. And we will spend most of our time talking about look level analysis, which is most of the people do with for social level analysis. But I will talk briefly on the graph level, and I will just give you how to do edge level analysis. For example, this is one example of the graph level analysis, which we call the density measurement. For example, we have 3 different networks here. This one is actually our network, the example network. And these 2 is different network that I created. For example, you want to see whether the nodes in your network are densely connected. Are they very closely related with each other? And you can use a measurement called density. For example, this graph will give you the density of 0.3. And this graph is 0.16. As you can see, the loops are actually not closely connected with each other. And this graph is give you a much higher density, but you can also see it visually that the nodes are actually closely connected with each other. Okay. And other graph level analysis is to do the correlation between graphs. For example, if you have same set of nodes and you want to, you can study the correlation between these two graphs. And if you want to study why edges are formed between two graphs, two nodes, you can use this edge level analysis called the ERGM, exponential random graph model. But unfortunately, this analysis can only be done with the network represented by the network package instead of the iGraph. Yeah. And node level analysis is much more important. And most of the people, when they are talking about social level analysis, they are actually doing the node level analysis. And one of the analysis that most people do is to calculate the centrality of each node in the network. And the centrality is actually the relative importance of a node within a graph. And there are many ways to calculate this kind of centrality. And I only have time to cover the degree centrality and the eigenvector centrality. The degree centrality is very easy to understand. For example, this node, number 5. You can count how many edges are forming in this graph, in this node. For example, 5, it form an edge with 4. It form an edge with 1. It connected with 2, and also 2 connected with 5, right? So the number of degree for the node 5 is 4, right? And we can make an assumption that if a node form a lot of edges with other nodes, it is important, right? But you can calculate the degree centrality of a graph using the degree function from the iGraph. But degree centrality have some problem. Can you imagine what is the problem?
The relationship is directed.
Yeah. For example, you are a spammer. You do spam, right? You do spam in Facebook. So you try to friends or with a lot of people, right? And then your degree centrality will be very high because you friend with a lot of people, right? But actually, no one friend with you, right? No one care about you. Or in Twitter or something like that, you follow a lot of people because you are a spammer, right? But your degree centrality will be very high, but no one follow you. So actually, you're worthless. So degree centrality cannot capture the relationship like that. So we need to use another kind of centrality measure, which is called the eigenvector centrality. And before I talk about what is eigenvector centrality, you can actually use the EV-cent function from the iGraph to get the eigenvector centrality. And after the calculation, you can get the eigenvector centrality like this. For each node, the eigenvector centrality is these values. And as you can see, number 2 and number 1 is actually very important. If you're talking about the eigenvector centrality. But for example, number 1 is only connected by 1 and 2. But still, it is considered to be very important by the eigenvector centrality, right? And I will still leave the definition of the eigenvector centrality in the later slide. But I want to show you how to use it first. Yeah, because I'm one of those people who believe that you know how to use it before how to the theoretical meaning of all those things, right? For example, you can calculate the eigenvector centrality of all nodes using these lines of code. It's just using the EV-cent function, and you need to specify your graph is directed, and then return the eigenvector. And you can plot the same example graph, and then you need to specify the vertex size is equal to the eigenvector centrality times a constant. And then you will get a graph that looks like this. And you can see that 1 and 2 is bigger now. And 5 is smaller, 3 is big. But 6 is very small because it is not important. So now we come to the definition of the eigenvector centrality. The nodes with high eigenvector centrality are those nodes who are connected to many other nodes, which are in turn connect to many others, and so on. Actually, if you look at the definition of the eigenvector centrality, it is a recursive definition, right? It's a recursion because you connect to the nodes that's connected to many other, and if you have a high eigenvector centrality, those kind of nodes also need to connect it to many others. You can see there is a recursion here. And I think the definition can be represented by these graphs. And the Google page rank, anyone know what is Google page rank? The Google is ranking their results based on the page rank, right? And actually, the page rank is a variation of the eigenvector centrality. And if you want to know more, you can read this paper. And actually, the page rank is just adding one particular variables called damping. But I don't want to talk about the damping here. For example, the size of the nodes in this graph is actually the representing the eigenvector centrality. For example, this node actually is connected by many smaller nodes, right? So it get a quite high eigenvector centrality, right? But this node is get an even higher eigenvector centrality because this node, which is connected by many others, is also connected to this node. You see the relationship, right? But this node is only connected by this yellow node here. Still, it will get a very high eigenvector centrality. Yeah, this is the trick. And yeah, as I showed you before, actually Google is using the eigenvector centrality or you can say the page rank in a information retrieval application. Information retrieval is a field in computer science talking about search. For example, when you search for the eigenvector centrality, it is actually ranking each particular page using something similar to this. You can imagine each node in this graph is a web page. And this web page link to another web page, right? And this another web page link to another web page. Yeah. And then the internet or the World Wide Web can be represented as a social network, right? And then after you represent the World Wide Web as a social network, you can calculate the page rank of each web page, right? And then you can use that page rank to rank the web pages, right? And Google making a lot of money using this kind of ranking. So you may, if you can master all those social level analysis, you can also make a lot of money as well. And finally, I want to present you a case that I want to represent. As you may know, I analyze the social network, the online social media, like Sina Weibo, but which is a perfect example of social network. But I don't want to use that as the case that I want to present today, because in Chinese we have a phrase called 走过行赢过行. If you do that field, you hate that field as well. So I want to choose another case that to represent to illustrate an application of social level analysis. You use R, right? So you will have to install some package, right? For example, this package called ggpod, which have some dependence and import and suggest, right? So ggpod actually depends on another package called stats, and also depends on another package called methods. And it's also import all these package. And it also suggests you to install all these package to use ggpod. And if you install this SP package, it is an enhancement for the ggpod. So this kind of relationship can be represented as a social network. And for example, ggpod depends on the method, and also it imports another package called Pyre. And it suggests you to install another package called hmits, and it's enhanced by this package called SP. And if you collect all these kind of relationship of all the package, you will create a social network, right? So the aim of this analysis is to rank the relative importance of our package based on the dependency relationship, right? So these are the steps that I use for this analysis. And first, I scrape the data from the CRAN. CRAN is is a web page that lists out all the package in R, right? But because R is not good for scraping data online, so I use Python. And then after I scrape all these data, I clean up the data using R. And for the rest of the 5 steps, I use R. I create a graph of the CRAN package using iGraphs, and then do the SNA, and then do the SNA, we get some kind of centrality, and then I use the centrality to rank all this package. And I try to do the test mining, but I don't have time. Yeah, I will just talk about it briefly. And for all the analysis, you need to have some domain knowledge about the analysis first, right? And for the R program, there are 4 different kind of relationship: depends, imports, enhance, and suggest. Depends and imports are important because, for example, if A package depends or A package import B package, if you haven't installed B package, you cannot use A package, right? But for enhance and suggest, if A package enhanced by B or A package suggests you to install B, you don't actually need to install B to use package A. So depends and imports are relatively important than enhance and suggest. So I will give more weight to the relationship depends and imports, and give lesser weight to enhance and suggest. And another domain knowledge is there are some package that we call the core R package that is not available from CRAN, but they are bundled with R. When you install R, this package are installed automatically for you. So I want to exclude all these packages because they must be important, right? Because they, yeah, there are just this many. 1, 2, 3. It have 5,000 something nodes, 5,000 nodes. Yeah. And also there is some other package that is called recommended package. For some platform, for example, Windows and Mac, they will also install automatically for you. But if you install a Linux version, they will not install automatically for you unless you install another package called hkrug recommended. So after I scrape all this data, I get a graph of 5,000 something nodes. And then I calculate the eigenvector centrality of all these nodes or all this package. And after the calculation, I get that the lattice, there is a package called lattice, which is for plotting, if you don't know. And also the mass is also very important according to the eigenvector centrality. And then there is another package called SU. These are the top 20. And if you plot, actually there is a function in iGraph called induce subgraph. You can extract a subgraph from the big graph of 5,000 nodes. And I just induce a subgraph of only the top 20. And then I get a graph that looks like this. And the size of the nodes is the eigenvector centrality. So you can see that, oh, the lattice and the mass and SU and survival, visually, you can see that, oh, these packages are important, right? And this is another visualization of the subgraph of the top 20. You can see that some nodes are red, in red color, right? Those are the recommended package. If you're using Mac or Windows, they will be installed automatically for you. So if you exclude also these recommended package, actually the most important package is this SU package. And also this Chrome, I don't know how to pronounce it, CHRON. and scale, higher, and ggplot. And then this GCPP are also important. This package is the package that you need to make some effort to install if you want to use it, right? And in case you don't know, Su, Chrome are two packages used for survival analysis, and ggplot is for visualization, and Pyre is for the SAC analysis. Yeah, meaning you want to separate your data into subset and then analyze each subset. Yeah, we have talked about Pyre in our previous R user group meetings. And RCCP is for integrate some C++ code in your R. This is the top 100. And you can see that the graph is actually difficult to see. Yeah, if you have something like 100 looks. And this is top 500. You can see that, oh, it's very complicated. And all you can see is just the labels, right? You can hardly see any nodes, right? Actually, you can control the display of the label. In this case, I just display the top 10 something, top 10 nodes with label, and all the others I just suppress the display of the labels. But still, you cannot see anything here, because it's difficult to interpret, right? And yeah, the following two slides are very theoretical, and it's a warning. And now I try to calculate the degree centrality of each node in the 5,000 nodes network. And then I plot the number of degrees, and this is the percentage of percentage of nodes with that particular degree. For example, number of degree. If that node with just 1 degree, it is 20%, right? 20% of the nodes just have 1 degree, and I need to emphasize that both the XY axis are log scale. Okay, and after you plot these graphs, you can see a straight line, some kind of a straight line, right? You can fit a straight line here. And this kind of distribution is called a power law distribution. And anyone have heard of power law distribution before? Okay, no. In the layman term, they don't like to call it power law distribution. They call it long tail. Yeah, I think most of the people have heard of the long tail, right? And it's actually meaning that, if you have a high amount of degree, you are actually very well, right? But most of us will just have a very small amount of degree. It's actually similar to the money distribution, right? Most of us have only very small amount of money, but very small percentage of people will have a lot of money, like Li Ka-shing or something like that. And the income distribution is also follow some form of power law distribution. Yeah, scale-free level. Yeah, and huh? Free. Oh, weight. No, in this case. Yeah, I haven't. Yeah. Okay. Yeah, I should tell you. For import and depends, I give 3. But for suggest and enhance, I give 1. When I calculate the eigenvector centrality, I also take into account of the weight. Yeah. And yeah, I've told you it's very theoretical. And the R package dependency relationship is actually following a thing we call preferential attachment, and or theoretically is follow this, I don't know how to pronounce, BA model, which is actually meaning that, oh, if you have a lot of degree, for example, you connected to a lot of people, a new guy will tend to also connect with you. Yeah, for example, if you have a lot of money, if you have money to spend, your money will also go to that rich guy, right? It's also like our society. And I do a very little simulation. This BA model will generate a model that with the preferential attachment element in it. So I generate a random graph with only 100 nodes, and then I try to plot it. Plot this random graph is actually very similar to the trend, the R package network, right? And then I try to plot the same graph. It's actually give me the straight line. Yeah, the very distinguished log graph, and then you get this straight line, so that we can see that, okay, the R package dependency is also follow this theoretical framework, the preferential attachment. And more thing you can do for the social level analysis. One thing is called, but I will not go through the details. One thing is called the brokerage analysis. For example, you can find out which node in the network is actually a booker. A booker is meaning, for example, you are a male and you are, let's say, in a social level of Facebook, you have some Chinese, you have some American people, and then you want to see which people actually will cross the border between the Chinese and then the American people. Those people are actually called a booker, right? And you can use iGraph to calculate the bookerage of each node, and then you will know that which graph is the booker. And a friend of mine actually do social level analysis in CUHK, and he actually used that study as his master study, and after he graduated, he published a book based on the brokerage analysis called 精英樂鬥, and it is available in the bookstore. It's an advertisement. And also you can study the network structure, let's say the centrality with some actual measurement. And for example, you can study the eigenvector centrality versus the view. In case you don't know, there is in the CRAN, there is a little field called view. For example, if this package is for survival analysis, in the view, it will say that, oh, it's available in the social level analysis field. For example, you can calculate the mean eigenvector centrality of each view, and then you can see that, oh, those packages working for you to do social survival analysis will tend to have a higher eigenvector centrality. And also you can also study the relationship between the description and the eigenvector centrality. And one particular study that I recall is a study studying a company, something like Enron. Anybody know Enron, right? Enron is, but It's actually not N1, but a company similar to N1 with some problem. They commit some crime in that company, right? And then they study the social network in that company, and then they find out that, oh, the centrality actually, okay, that company commits some crime, right? So all the people will be go to court, and then the court will say, oh, you are sentenced with a 10-year trial, a 10-year in the jail, right? And then they find out that, oh, the centrality is actually related to the punishment you will receive from the court, because you get a lot of information from your social network, right? But you also commit some crime. And if you get more information from that social level, you are more likely to commit more serious crime in that social level. So it is actually related to the punishment you will receive from the court. And I can tell you, a lot of research on the social level analysis is doing something like this. And finally is the community hkrug detection. For example, you have a social network. You want to see is there any hidden community within that social network. You can use those kind of community detection algorithm to detect some kind of community in your big network. And in the finally, I want to show you test mining, but I just do it briefly. And I want to study which keywords. This is the description in that particular package. And I also scrape this description from using our Python. And I want to see which keywords in this description will actually determine your eigenvector centrality, meaning which keywords will make you more important. And in case you don't know, it is actually something the people doing for the search engine optimization, SEO. They are doing something like this. And because I don't have a lot of time, actually I have all the data, but I don't have time to analyze it. I just use the feature selection using the bivariate correlation, meaning I study each keywords in my database, and then if that keywords appear for a particular package, I study whether that phenomenon also correlate with the eigenvector centrality. And I found that, oh, keywords like introduction, typical, or flexible, or handling, editing, if your package description have these words, your package will also tend to have a higher eigenvector centrality. Yeah, and if I have time, I will do a more sophisticated analysis taking into account the interaction between those keywords. Yeah, I think this is the end of my talk. And I can show you some code. Oh, before that, any question?
So I think in the scenario of money laundering in bank,
Yeah.
seems that we can make use of this kind of social network and like looking at the money flow of different accounts.
Yeah.
Then we may observe some kind of I mean very dense flow into a particular account, and that may be doing some abnormal activity.
Yeah.
Yeah.
Actually, FBI or CIA is doing a lot of SNA as well, but they try to anti-terrorism, study terrorism, which people are actually terrorists. So they study the communication between different radical groups in say Saudi Arabia, and then they also do something like you say, they do a SNA and then find out which which particular groups are actually having a lot of communication with all those radical people. And then the CIA will pinpoint that particular group as a group that they need to do something. Yeah, and yeah, it's used a lot in law enforcement as well. Yeah, and for your case, it's actually very feasible to do it with the social level analysis. Yeah.
Is there a function that traces the path from?
Yeah. Graph transversions, like shortest path. Yeah, in iGraph you can do all of those things, but not necessarily the fast algorithm for finding the shortest path.
I want to do gene expression in network actually. Yeah. But once I have a network, biologists tend to work in pathways and they tend to go.
Yeah.
So I want to try to convert it back to a pathway. So I don't need the shortest. I actually just need.
Yeah. You can find. I think you can find all the pathway. Oh, okay. Yeah, and then you can select which one is. Yeah. iGraphs. Yeah, it do all analysis about social level analysis, and actually iGraph is also available in Python and C if you don't want to do it in R. Yeah.
And also, you imported it in the weights way, but you input an adjacent matrix that would do this. Like when you showed us, you input the source and the destination and then the weights.
Yeah.
But if you had just an adjacency matrix,
yeah,
it would also.
Yeah. If in the adjacency matrix, the weight will be actually the numbers. For example, it's so good that we have this one will be actually the weight. In most of the time, you will not use the adjacency matrix to import your data because it tends to be very big. The data will be very big, and it takes a lot of time to process. So most of the people will use the edge list. Yeah. And back to your questions about the path. Yeah, I have a lot of. This one is to find the shortest path, and I believe there is another function that will find out all the path. Yeah, because when the function need to calculate the closeness centrality, it need to calculate all the path. Yeah, because it need to calculate all the paths, so you can imagine that the closeness centrality will take a lot of time to calculate. Yeah. And for those who are very good at linear algebra, but I'm not one of those people, and the eigenvector centrality is to calculate the eigenvector of this adjacency matrix and extract the first eigenvector. Yeah. I'm not good at linear algebra at all, so this is what I know. Any more questions?
Talking about scraping data from internet, is better to use Python?
If that particular website provide an API, let's say Twitter, something like that. There is no difference for you to use Python or R, because both of them are just using the curl to do that. But if you are talking about scraping the raw HTML file, in my opinion, it's better to use Python, because Python have two very powerful packages. One is called Beautiful Soup, another is called LXML. Both of them are very good at parsing HTML file. So I use them a lot. But for R, if you need to do the scraping, you need to use a package for XML. But that package is not so good. Yeah, because it has a lot of problems parsing HTML table, for example. Yeah, and I can show you some code. Okay, this is the first step. Is actually some Python code, and as you can see, it's importing a package called Beautiful Soup. But because this is not a Python user group, so I just go through it briefly. It's just first, you go to the index to get all the package names, and then get the first page of each package, and then scrape all the data, depend, suggest, import, in view version, license, something like that. And then it will export the data as a big CSV file. Okay? And then the second, how much time? Oh, okay. Actually, the time is very, it should be very fast, but because of I'm a nice person, yeah, I don't want to overflow their server. So after I scrape one package, I wait for 10 seconds, something like that. Yeah, it's better to be polite, right? So a lot of time will be used for waiting for doing something like that, and I usually do it in the midnight, so it doesn't matter. So because I will not work at midnight, I just order the computer to do that in the midnight, and then in the morning after I can get the data, right? And after the scraping, I get a big CSV file, and that CSV file is also available on this GitHub here, which is about 2 megabytes. For some people, this is big data, but for me, it's not. And I generate the edge list using some test manipulation, and then after the analysis, I get the edge list, and then I convert that edge list into a graph here, and then I give the weight for each edge, and then I calculate the eigenvector centrality here. And then this big function is for plotting all those subgraphs. And if you have time, you can study it. And I plot all these different kind of subgraphs. And then for this graph, is plotting the top 20 package according to the eigenvector centrality. And this part is doing the test mining. Actually, I'm planning to, if you guys interested, I can talk about test mining in the coming meeting. And text mining is just, yeah, for my analysis, it's just you have a big chunk of text, right? And then we want to convert that big chunk of text into a thing we call the document term matrix. Do you know what is document term matrix? It's actually meaning, for example, the document 1 have that particular terms. So if it is available in that document, we will denote it as 1. It's some very similar to the adjacency matrix. But you need to do a lot of processing. For example, you need to remove some stop words. In my work, I do the text mining of Chinese texts, but in this analysis, I'm studying the English. But if you want to study the methodology for doing text mining for English and Chinese is very different. But yeah, because English have space between each words, right? But Chinese you don't have it. So you need to have some mechanism to separate the Chinese text, a bunch of Chinese text into vocabularies, which is difficult, which is a difficult problem. But for English, it's easy. You just separate each text with based on the space or the punctuation mark. And after that particular step is called tokenization. After the tokenization, you need to remove some words, which we call the stop words. Stop words is just some very commonly occurring words like to, and, or is, something like that, because they usually carry low information for your analysis. So we need to remove them. Depending on your application, sometimes you don't need to remove, but for this particular analysis, I just remove all those stop words, and then remove all those punctuation, and then do a step called stemming. If we have time in the future, we will talk about what is stemming. Stemming is like, for example, regularized regression. The word regularize, we will remove IZED from that word. For example, regularization, we will also remove those station, so that we will also retain the regular as a stem. And then we convert your big bunch of text into a document term matrix, and then I study the frequency of each terms and the eigenvector centrality using correlation only. And this graph is actually doing that, and this file graph is doing the two very theoretical graph of power law distribution. Yeah. This is pretty much all I want to say for today. Yeah. Any more questions?
And then good package for Chinese text mining.
Oh, good questions. For text mining, if you are doing in R, pure R, there are, yeah, if you're talking about Chinese text mining, the only difficult problem is tokenization or text separation, adding space in between the vocabularies. In R, there is a package called TMZ, I guess. Which is doing, I forget the actual name, something like that. It's actually just a wrapper for some Java function to do the text tokenization. And after you do the tokenization, you can use TM to do the actual text mining. But for my study, I use a mixture of Python and R to do that. And I use a package from Python called Jieba to do the test tokenization, but which is not good because I need to switch from Python to R and R to Python all the times. So one of the projects that I'm doing is to wrap some C++ code of they're doing Chinese separation or Chinese tokenization into some R function, so that I can do all of my job in R. Yeah, I'm still working on it.
social network analysis uses and like
trial of inspection in what? In disease. Yeah, for example, some disease like AIDS, you know, AIDS is transmitted within a social level.
Yeah.
For example, a guy who have AIDS and then doing some, they share needles. I use a non-obscene, yeah, share needles with each other. Yeah, and they will very likely to also get AIDS, right? So what the researcher usually do is to first construct a network of needle sharing, another network of AIDS transmission, and then do a correlation between these two networks using something they call QLab analysis, and then based on this, you can adjust for the effect of the social relationship, but you can infer or you can prove that needle sharing is a risky behavior, and it will make you infect with disease. And some people even use the social level analysis to study chronic disease, like obesity. There is a very famous Lancet study talking about obesity actually is infectious. For example, if you have a lot of friends that is obese, you are very likely to be obese as well, because you are sharing some kind of behavior, because the behavior between you and your friends will be very similar, because obesity is very related to your behavior. So they after they do the social level analysis, they conclude that obesity is also infectious. And flu, the people from the School of Public Health in Hong Kong U, they are doing a lot of social analysis of the infection of flu. So yeah, it's very, they do a lot of them. But for the AIDS things, is doing in the CUHK, School of Public Health, because they have a professor that is very interested in a phenomenon called men have sex with men. So they do a lot of research on this. Yeah, they collect a lot of data about the gay people in Hong Kong. Yeah, they make a lot of effort to collect all those data. Yeah. Yeah. Any more questions about social level analysis? If no, we will move on. And first, I want to stop the Hangout. Oh, goodbye, YouTube.